Hello, 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 everybody, and welcome back. Thank you for joining me. We're looking at question number 8 on our 2011 Euclid paper. The sieve, or sieve, of Sundaram uses the following infinite table of positive integers. So we got 4, 7, 10, 13. So that's going up by 3s, it looks like. And then, we got the same sort of thing going on. In fact, the whole thing is sort of symmetric on this diagonal. Looks like they're going to tell us a bit more about this. The numbers in each row of the table form an arithmetic sequence, the going up by 3s here. The numbers in each column of the table form an arithmetic sequence. Now, is it always going up by 3s? No, these ones are going up by 5s. These going up by 7s, these up by 9s. Okay. And so it's symmetric, so these ones are going up by 9s as well. The first 4 entries in each of the first 4 rows and columns are shown. Okay. So going up by 3s, 5s, 7s, 9s. So the amount that you're going up by follows an arithmetic progression as well. So A, determine the number in the 50th row and 40th column, which we can do. Now, if I just very quickly look at B, which is something you might want to do for these written questions where they introduce a brand new concept to you. It might be a good idea to look at all 3 of the questions together to sort of give you a direction as to what you might do. But if I look at B, I see determine a formula, and that caught my eye, which is why I'm looking at B. But determine a formula for the rth row and cth column. So if I answer B, I can just plug in 50 for R and 40 for C. So I think I'm just going to try and do that right away. Now, it's a written question, so I do need to first set it up so it's not in continuous mode. There we go. So we do need to sort of explain what we're doing. So I would say, notice that in the rth row, the arithmetic sequence, let's say, goes up by. Now, what exactly do we go up by? So it's 4 and 7. So we go up by 3s if you're the first row. We go up by 5 if it's the second row. 7. So is there a way to base formula for what we go up by on R? So if it's the first row, how do you get 3 from R? I notice I go up by 2s for each of these. So increasing R should increase something by 2. So I'm going to say 2R plus 1. And so second row, that would be 5. Third row, that would be 3. Okay, so that's good. So I know what we're going up by for my arithmetic sequence in the rth row. And now, so, can we also determine the first term? So if we're going up by, well, the first term is going to be over on the absolute left-hand side. So we're going up by 3s for that first term. So the first term is 4 plus 3 times R minus 1. Because if R is 1, we want this to be 4. I guess we could say this is 1 plus 3R. I mean, I suppose that's our way to do it. But I'm fine with my answer. Oops, not on the erase tool. So, the first term is 4 plus 3R in this row. Okay, these are nice observable facts. I'm pointing them out. That counts as me writing up my solution. I don't have to super justify these. I suppose if you wanted to, you could say, well, the first term is in the first column, and the first column, like the first row, goes up by 3s. That would be fine. So the term or entry or whatever you want to call it in the rth row and cth column is the Cth term in this arithmetic sequence. And so how do you find the Cth term in an arithmetic sequence? Well, normally arithmetic sequences look like this. A plus a constant term, A plus twice that constant term, A plus 3 times that constant term, where A is your starting number. Well, I've got my starting number, and D is how much you go up by. Well, I know how much we go up by, 2r plus 1. And then, okay, well, the first term is just the A. The second term is A plus 1D. The third term is A plus 2D. The fourth term. So if I want the Cth term, it would be A plus C minus 1D. So now we can turn that into a nice little formula. And is seen to be... So my starting term plus C minus 1, however much we go up by. Okay, so there we go. I've explained sort of where it's coming from. I picked out my first term. I told them how much I go up by. So this is a nice sort of clean explanation. But I get the feeling that this probably could be a little cleaner. I mean, just from the fact that this table here is so nice and symmetric, if I swap all the C's and R's, I should get the same expression. And it doesn't look like that here. But what could we do? We could expand this out 3r minus 3. And then 2rc minus 2r. And then plus c minus 1. Now the 4, the minus 3, and the minus 1 will cancel. 3r's and minus 2r's will cancel, leaving just 1r. So we should get r plus c plus 2rc. This is very nice. This is symmetric in r and c. If I swap all the r's to c's and c's to r's, I still get the same expression, so that's good. Now what we could do is, well, we've got the table here. Oops, wrong button. We've got the table here. We could sort of pick it out. How do you get this 17? Well, it's in the second row, third column. So that would be r is 2, c is 3. So if I do r is 2 and c is 3, I'll get 5 plus 12, that's 17. And if I wanted more reassurance, I could double check these with some more, but I'm happy with my answer here. Okay. Didn't run into any sort of complications. But if you want to, test things out. Now, there's no reason I had to swap it. I could have just left it like this, but I like a nice clean thing that I can plug in. So that solves B. So now if I say returning to A, the term in, I think it was the 50th row, 40th column. I mean, it's going to be the same if it was 40th row and 50th column. Is 50 plus 40 plus 2 times 50 times 40. So that's 90 plus 100 times 40 is 4,000. So we're looking at 4,090. Okay. Yeah, and it was 50th row and 40th column. Okay, so we did A and B really quickly, sort of just by doing B. Okay, so it pays to look ahead a little bit. Now, C part. Prove that if n is an entry in the table, then 2n plus 1 is composite. So composite numbers are not 1 and they're not prime, which means I can write them as sort of two separate factors, or I can sort of factor them into things that are not 1. Okay, so what can we do here? Well, if n is in the table, or the sieve, then we can find r and c so that n is equal to r plus c plus 2rc. I mean, that's what it means to be an entry in the table. You're in some row and some column, and this gives me the formula for that. Okay. So 2n plus 1, well then that's going to be 2r plus 2c plus 4rc plus 1. And we want to show that this is composite. Well, if I rewrite it like this, I think, yeah, we should be able to factor this into 2r plus 1 and 2c plus 1. So the 1 and 1 would give me the 1, 2c and 1 gives me 2c, 2r and 1 gives me 2r, and the 2r, 2c gives me the 4rc. So that works out. I just need to explain why neither of these are 1. So we'll have both r and c greater than or equal to 1. So 2r and 2c are greater than or equal to 2. 2r plus 1 and 2c plus 1 are greater than or equal to 3. So neither factor is 1. So 2n plus 1 is composite. That was not that bad, actually. Okay? But there probably was a mark. Like, it's all well and good to say you factored it, but there probably was a mark trying to explain why these factors are neither of these are 1, because that's crucial. Okay? If we were numbering our columns and rows starting from 0, we'd have a bit of a problem because there'd be a chance that you would get some primes. Okay, so we do need this extra little step explaining, hey, the factors that I just got out of this formula, and this is a sort of a very common factoring, I've seen it in a number of places. You can also get a similar thing, just while I'm thinking of it, with minus signs in here, which is kind of cool to note. And you can also do like a minus sign here and a minus sign here, and get a minus sign here, but still have a plus sign here. And those are some cool extra little things, but it's a nice little factorization. It comes up a fair bit, and that's why I was able to pick it out so quickly. But we do need to say, okay, we've got this way to factor it, but these definitely aren't 1, so 2n plus 1 really is composite. Now, if I wanted to double check that I've done all my work here correctly, we could say, well, hey, I know 17 has r is 2 and c is 3. Now, 2 times 17 plus 1 is 35. Does that really factor as 2 times r plus 1? 5. Times 2 times c plus 1, which is 7? Well, yeah, it is 5 times 7. So it looks like this factorization really works. And if you are having trouble trying to find this factorization, because maybe you can't see it quite clearly, what you could do is you could go back to the table here and start saying, well, okay, I know for a fact 13 is in there. 13 times 2 plus 1 is 27. How can I factor 27? 22 times 2 plus 1 is 45. How can I factor 45? And in fact, if we go by rows, the 2 times 7, that'll give you 15. The 2 times 12 plus 1 will give you 25. And then 35, and then 45. All of these have a factor of 5. And then you might make the connection, hey, what do you go up by in this row? 5. That's kind of interesting. What do you go up by in the row that's got 7? 3. This is 3 times 5. So if you need to do a little bit more digging, if you're not immediately someone who's able to say, aha, that must be factorizable like this, you can still poke around and you can still find the sort of expression that you might be looking for. It just requires a little more experimentation, a little bit of exploring of some of the other values in the table. Now, I don't think there's no D part, so I guess we're done with question number 8. I liked that question a lot. I was expecting something a bit weirder, but it was nice to see. Up next is going to be question number 9, so if you'd like to, give that one a try and then join me for that in the next video. Until then, take care.